So, welcome. We had seen many important concepts in the last lecture. One was diffusion of A through stagnant B. Another one was time scale for diffusion. We had done 1D conduction, 1D diffusion, and unsteady state diffusion through a slab. That allows us to get time scale for diffusion. Two very important concepts we have done. Before that, we had seen two more concepts. One was interfacial area per unit volume, and another one was number of transfer unit and height of transfer unit. So all these concepts we have looked at. So revise them. Let's go to this last part now. We are on mass transfer. Just to quickly revise what is meant by diffusion of A through stagnant B. Derive an equation for flux of A for this situation. What is Fourier number for heat transfer? Fourier number for mass transfer. Write expressions for time scale for diffusion of heat or mass transfer. If you answer this, automatically your revision will happen and you can be ready. So again, to remind you, these are the equations. This is our methodology. This lecture, what we are going to do is look at this second part. You had used empirical equations for solving problems. Just Sherwood number equal to something into Reynolds number, something into Schmidt number, and so on and so forth. In this class, we are going to look at how to estimate mass transfer coefficient using theories and analogies. Excuse me. What these theories do is to provide a mechanistic view of the mass transfer process. So if your boundary layer is like this, if your boundary layer is like this, let's just pause for a second. Yeah, it is moved a little bit away. You can read the letters. So boundary layer consists of viscous sublayer, buffer layer, turbulent core. So imagine this was the wall through which mass transfer is happening, across which mass transfer is happening. Mass transfer is happening from that wall to the bulk. There is a laminar sublayer, there is a buffer layer, there is a turbulent core, and throughout total, sum together total of this is the boundary layer. Now mechanism of how mass transfer occurs is different in different regions. In the laminar sublayer there is no turbulence. So mechanism is purely by molecular motion. Remember when we had done universal velocity profile, we only took viscosity here. We only took mu dvx by dy here. In the boundary layer, in the buffer layer, we took a combination. Actually, we took only the turbulent part, like as if it was a turbulent core, right? And in the turbulent core, the contribution of viscosity or contribution of molecular diffusion now is very small. All the mass transfer occurs because of the movement or because of the eddy motion. Okay, and in the buffer layer, it is some combination, both progressively viscosity is less and less important. Progressively eddy diffusivity is less and less important in those particular directions. Less and less important as you go away. Viscosity is less and less important as you go away from the wall, from the place where mass transfer occurs. Turbulence is less and less important as you go towards that laminar sublayer. So these theories are a simplified version, simplified models of this mechanism. This is the correct picture. Theory is just a simplified version of this. First theory is called as Whitman film theory. Okay, what this theory says is entire resistance to mass transfer is within a fictitious stagnant film, which means if this is the concentration profile, actually we are going to visualize it like a layer. All the resistance is accounted for here, so therefore there is no further change in the concentration in this layer, in this part, and this fictitious layer we call it as a mass transfer film. And concentration profile, thus, because entire resistance is here, is therefore linear if only pure diffusion is occurring. And mass transfer coefficient, therefore we can write, because it is stagnant, only molecular diffusion is occurring, Km would be diffusivity divided by delta. It's easy to visualize, so it's useful because it's easy to visualize, and we use this when there are two films. So for example, there's gas liquid mass transfer flow, gas absorption or distillation. We have a liquid side mass transfer resistance, we have a gas side mass transfer resistance. To help you to visualize, we use this film theory, and then we just use the mass transfer coefficient. We don't actually use the thickness delta anywhere. We just say that mass transfer coefficient multiplied by the concentration difference is the net flux. Okay, this theory proposes, I mean, this theory obviously from here says that if diffusivity increases, mass transfer coefficient increases in linear manner. If diffusivity doubles, mass transfer coefficient doubles. That's not what really is observed experimentally, right? So that's why this theory is limited. It does not have a correct dependence of diffusivity on the mass transfer coefficient. Higby in 1935 proposed a theory. That theory was like this. So imagine this is our boundary layer. What this theory proposed is that there is an eddy that comes from the bulk. It comes to the interface where mass transfer is happening. It stays at the interface for some interval of time, let's say Tc, that's called as contact time. Within that time, it stays there. Mass transfer is happening from that surface to this eddy, and after this contact time, it goes back into the bulk. And when this goes back, another eddy takes its place, and this process continues. Different eddy come, spends the time Tc, goes back. Another eddy comes, spends the time Tc, goes back. And during this time, we have one dimensional unsteady state diffusion into this eddy. That's why we solved that problem in the last lecture. Okay, so this packet or eddy is treated as a semi-infinite with respect to mass transfer penetration depth. This packet goes back into the bulk liquid and mixes, and all packets have the same contact time Tc. So if you solve this equation with respect to boundary conditions for a time duration Tc, we are not going to do that, but you can derive that mass transfer coefficient is 2 square root diffusivity divided by pi divided by contact time. Okay, so it's useful when there is a clear cut definition of a contact time. So for example, if there is a film, if there is a liquid film falling, we solved that problem in our momentum transfer class. When we had a wall, liquid was flowing down a film, we calculated thickness of the film. Right? So contact time, then it can be very straightforwardly calculated. Time required for liquid to flow from start of the plate to end of the plate. That's a contact. So it is useful, this theory is useful when you can define contact time very accurately, like that film. Or we have bubbles or droplets which are rising or falling. So if a bubble is rising, let me just help you to visualize. So imagine this is a bubble. This bubble is rising. It is as if the flow of the liquid relative to the bubble is like this. So if an eddy comes here, if an eddy comes and sits here, let's say, let me draw another color. So let's say liquid is flowing down, there is an eddy that comes here, and then that eddy slides from here to here. So what will be the contact time? Will be the time required for that eddy to go around the bubble. How will you get that? This distance divided by the rise velocity of the bubble. Imagine that if you are on a platform, train is going by. Contact time of you with train is the distance divided by the speed of the train. It is the distance through which that bubble travels, or the fluid travels with respect to the bubble, and divided by the rise velocity of the bubble. Or it could be a solid particle which is settling down. Exactly same thing will happen. Solid particle settling down. Remember the sugar problem. The liquid is going around like this. I told you that the relative velocity is the terminal settling velocity. That's why relative velocity is the same as terminal settling velocity. Now if an eddy is there, a solid particle is settling, so eddy is here. Let's say one eddy comes, or a packet of fluid comes here. When the solid particle is going down, this eddy or packet of fluid will travel like this. So the contact time is time required for this packet of fluid to go around. it will be half the perimeter of this circle, if you like, divided by the velocity, settling velocity of that particle. So that's why settling terminal velocities are important. They allow you to calculate mass transfer coefficients. And another advantage is this theory predicts a more accurate description of how K depends on mass transfer coefficient. If you increase the diffusivity by a factor of 4, mass transfer coefficient will only increase by a factor of 2. That's more realistically observed. Okay. Another theory is called a surface renewal theory, proposed by Danckwerts in 1951. There is a picture of Danckwerts near our library. Okay, there is also a book in our library written by Danckwerts. So it is that important that ICT thought of having a picture near the library, picture of Danckwerts near the library. Pioneering work on surface renewal theory. So what this eddy proposes, or this theory proposes, that eddies come to surface as if to renew the surface. Imagine, visualize. Okay. Suppose there is a surface like this. Eddy comes, goes. Eddy comes, goes. Another eddy comes, goes. As if it is this surface, it is clear, wiped, refreshed. Every time, fresh surface. So let's say, for example, if you have, let me give you an example. Imagine that this is a metal and there is a rust, right? So that rust prevents prevents further contact of oxygen. So if I rub this surface, if I refresh the surface, more oxygen can react, more can rust, right? So it's as if there is a refreshing. As if I want to, as if the air or the fluid in the vicinity, it is getting stale by mass transfer from this surface. So if I have an eddy, it refreshes the surface. So that's called as a surface renewal parameter. Okay. And then the average surface renewal rate, S, is defined, and the rate mass transfer coefficient is defined as square root diffusivity divided by the surface renewal parameter. Again, this theory proposes a better dependence of K on DM. There are other theories, we are not going to go into that. These are just some of the basic theories that I wanted to show you, that fundamentally, mechanistically, if we approach, we can calculate mass transfer coefficient. That's the message I want you to take. Little bit about analogies, right? We talked about theories. Very briefly about analogies. Okay. So we talked about boundary layer. So imagine there is a momentum boundary layer, there is a concentration boundary layer, and there is a thermal boundary layer. So imagine there is an eddy here. This eddy comes and goes here and transfers its momentum. Eddy goes from bulk to the interface and exchanges momentum, or eddy goes from bulk containing some concentration, goes to the surface, exchanges or releases concentration or transfers material. So mass transfer. Eddy from the bulk goes here, enthalpy is higher here, enthalpy is lower here, transfers enthalpy transfer. So if you think about all such eddies, the motion of eddies, the volumetric flow rate brought by all these eddies per unit surface area, can we not think of this as a velocity of the eddy? Think about this. So many eddies are coming per unit time, per unit area. Per unit time, per unit area, volumetric flow rate is nothing but velocity. So velocity of this eddy is nothing but volumetric flow rate per unit area. Okay. That will allow us to calculate the rate of momentum transfer, rate of mass transfer, and rate of heat transfer. Here is the analysis. So rate of momentum transfer per unit volume, rho into V infinity in the x direction. Rho into V infinity. That's the momentum that this eddy is carrying in the x direction. When it travels to the surface, volumetric flow rate per unit area that it travels with is this V eddy. So transfer of momentum per unit time, per unit area is rho V infinity V eddy. Momentum transfer, macroscopic balances, lectures 2, lectures 3. So that's nothing but tau W. So tau W is rho V infinity multiplied by V eddy. Divided by half rho V infinity square, it will be 2 V eddy divided by V infinity. So friction factor is nothing but 2 V eddy by V infinity, or Eddy velocity, we can think about this as V infinity divided by multiplied by F by 2. That's the picture. Friction factor. Rate of mass transfer, if you want to write per unit area, is the concentration difference multiplied by the volumetric flow rate per unit area. That tells you rate of mass transfer per unit area. That's nothing but flux. So flux is nothing but V eddy multiplied by Ca infinity minus Cas. Flux divided by Ca infinity minus Cs is nothing but mass transfer coefficient. So mass transfer coefficient is same as the eddy velocity. Eddy velocity we can calculate from here. We can put that from here in terms of V infinity. That's, we don't want to measure eddy velocity. We want to measure V infinity. We can measure friction factor, right? So K would be F by 2 V infinity. Make this into Sherwood number multiplied by L divided by dm. F by 2 V infinity L by dm. So left hand side is Sherwood number. F by 2 V infinity L multiply and divide by rho and mu. You see, now this is Reynolds number and this is Schmidt number. So Sherwood number is related to Reynolds number, it is related to Schmidt number, and F by 2 friction factor. You see now the analogy, the meaning of the word analogy. Analogous. Momentum transfer and mass transfer is analogous to each other. Analogous to each other. Eddy motion. Eddy motion. We can get mass transfer, dimensionless mass transfer coefficient. That's the meaning of Sherwood number. It's a dimensionless mass transfer coefficient. That comes from momentum transfer. F is a momentum transfer parameter. Same way for heat transfer, if you do, rate of heat transfer per unit area is nothing but rho Cp T infinity minus Ts. That's the enthalpy per unit volume, extra enthalpy per unit volume that it is bringing. Rate per unit area is nothing but velocity. So flux would be velocity of the eddy rho Cp T infinity minus Ts. I can divide by T infinity minus Ts. That's nothing but heat transfer coefficient. You will do this in your heat transfer course. H is equal to V eddy rho Cp. V eddy we can write from here. V eddy we can write from here. It is friction factor multiplied by V infinity. Rho Cp. Make H also dimensionless. Like Sherwood number, we can make H also dimensionless. HL by thermal conductivity. You see the analogy. KL by dm, HL by KT. Heat mass transfer coefficient, heat transfer coefficient, length, diffusivity for mass, conductivity. Right? You can write as F by 2 V infinity L rho Cp by KT, and then V multiply and divide by mu. Right? Let me multiply by mu and divide by mu. So VL rho V infinity rho L by mu, that's our Reynolds number. Cp mu by K, that's our Prandtl number. Nusselt number, dimensionless heat transfer coefficient, is related to Reynolds number and Prandtl number. Analogy. Momentum transfer allows you to calculate heat transfer coefficient, Nusselt number. Both these cases, the Sherwood number dependence on Schmidt number and Nusselt number dependence on Prandtl number is not as per observation. Why is that? It's not as per experimental observation. Why is that? Because we have assumed eddy goes right up to the wall. That's not what happens. That's not what happens. What happens really is there is a laminar sublayer. There is a buffer layer. Eddy goes up to the buffer layer. Then it partly becomes a molecular transfer. So other analogies later on, after this Reynolds analogy, von Karman 1939 gave an analogy considering this laminar sublayer and buffer layer. considers molecular transport in laminar sublayer, both in laminar sublayer and in the buffer layer, and eddies in the turbulent core. They can travel up to the buffer layer. We are not going to do this, but this you can calculate. Sherwood number is going to be, CF is nothing but friction factor. It is just that book is giving CF, it is nothing but our friction factor, F. Right? This is nothing but F. Friction factor. This book calls it as CF, but it is nothing but friction factor. You can derive this. We are not going to do it, but this can be derived on Karman analogy. Those who are interested can look at it. Now, this provides a better approximation on how Sherwood number depends on Schmidt number. It's not linear dependent. There is Schmidt number in the denominator as well. It's not, Nusselt number is not related linearly to Prandtl number. There is Prandtl number in the denominator as well. This predicts a better approximation of what happens in reality, how Sherwood number depends on Schmidt number, how Nusselt number depends on Prandtl number. Point that I want to make is that these analogies give you a basis for why Sherwood number should depend on Reynolds number and Schmidt number. If you want, let's go back here, right? We can make this into Sherwood number. So KL by diffusivity, molecular diffusivity, right? Or D if you want. I can take this L and dm inside. I have multiplied both sides by L and dm. L square dm by Tc. Tc we can write it as L divided by V, some length scale divided by some velocity scale. So this L will cancel out. This will be, forget that pi just now, 2 square root. This will become L V dm. Pi is there right now. Forget that pi just now. I can divide by rho and multiply by mu. Right? Multiply by rho, divide by mu. Both. Right? This is now Reynolds number. This is now Reynolds number. Right? Oh, what happened? Oh, our dm square was not there. Sorry. This is dm square. I just did for L, I have to do for dm square as well, and then dm will cancel, so this dm will not be there. There will be dm in the denominator. Reynolds number, Schmidt number. Reynolds number raised to 0.5, Schmidt number raised to 0.5. Sherwood number. So these theories as well as these analogies, they tell you why logically there should be a relationship between Sherwood number, Reynolds number and Schmidt number. And they give you a functional dependence as well. Okay. Chilton-Colburn, another analogy, 1933, is approximately same time, but this is based on experimental observations, right? So this Sherwood number divided by Reynolds number divided by Schmidt number, we call as another number Stanton number. Sherwood number divided by Reynolds number and Schmidt number. That's called as Stanton number, S-T-A-N-T-O-N, Stanton number, S-T. So this Chilton-Colburn analogy, what it does is says it that this Stanton number, it defines a parameter Jm for mass transfer as Stanton number into Schmidt number raised to 2 by 3. And it says that this Jm parameter is equal to F by 2. Now if you substitute for Stanton number, Sherwood number, Reynolds number, Schmidt number is F by 2 into Schmidt number raised to minus 2 by 3. So Sherwood number is F by 2, Reynolds number, Schmidt number raised to 1 by 3. And if you say friction factor is 0.046 Re raised to minus 0.2 like Reynolds, like for turbulent flow. Recall that lecture, friction factor versus Reynolds number chart. If you substitute that, you will get Sherwood number is equal to 0.023 Re raised to 0.8, Schmidt number raised to 1 by 3. This equation we have used for the pipe flow example where there was a pollutant being degraded in the pipe. I gave you a Sherwood number expression. This was that expression. Okay? Instead of 0.83 there, it is now 0.8. So that's a small error change. Right? Or if you want to think in terms of heat transfer, Nusselt number divided by REPR is Stanton number. JH factor for heat transfer is Stanton number into PR raised to 2 by 3. Rearrange that, you will get Nusselt number equal to F by 2 RE and Prandtl number raised to 1 by 3. Put F is equal to 0.046, RE raised to minus 0.2. You will get Nusselt number is equal to 0.023, RE raised to 0.8, Prandtl number raised to 1 by 3. This equation is very, very, very important. Without this equation, you can't move a step forward in heat transfer. You will see that when you start doing heat transfer. So point that I'm trying to make is this is a dimensionless mass transfer coefficient. It tells you how it depends on Reynolds number and Schmidt number, and why it should depend on the Reynolds number and Schmidt number, because the boundary layer, that is the phenomena involved. That's why momentum boundary layer, thermal boundary layer, concentration boundary layer, the ratios of those boundary layers, that Schmidt number. I want to re-emphasize some of the concepts that we have dealt so far in the mass transfer part. First of all, let's talk about diffusivities. These are molecular diffusivities, stagnant medium. Remember, when we say molecular diffusivity, it is a property because of arising out of molecular motion. We talked about diffusivity in gases. Here is the data from, of course, Bert Stuart Lightfoot's book. You can see that it's in chapter 17, so table 17.1-1. Couple of things I would like to emphasize. So this tells you the diffusion in a pair of gases. So when you say A and B, A is the component that is diffusing, B is the medium in which A is diffusing. So for example, when we take CO2 and nitrogen, it is the diffusivity of carbon dioxide gas in nitrogen gas. And you can see a couple of things. First of all, the values of Schmidt number that are given here, the values are given as mole fraction of A tending to 1 or mole fraction of B tending to 1. So this will be like the Schmidt number for pure carbon dioxide in this particular case, 0.48, and this would be like the Schmidt number for pure nitrogen in this particular case, 0.91. Okay. So now, and this is of course at a particular temperature. Couple of things I would like to bring to your attention. So first of all, let's look at this carbon dioxide diffusion in nitrogen. The value of diffusivity is 0.144 centimeters square per second. So this is like 1.44 into 10 raised to minus 5 meters square per second. Remember, we have talked about diffusivity in gases of the order of 10 raised to minus 5 meters square per second. So this tells you that these are the kind of values. Second point to notice from this table, if you compare any particular pair of gases and dependence of temperature, so this is like 0 degrees centigrade, this is like 25 degrees centigrade, you will notice that the diffusion coefficient, diffusivity value, so diffusivity value DAB is increasing with increase in temperature. Okay, that's the second point to sort of note. Third point I would like you to emphasize, to you is compare this value and this value. So 0.144 versus 0.674. So this value is 6.74, if you like, 6.74 into 10 raised to minus 5 meters square per second. Okay. Compare. So CO2 diffusion in nitrogen, diffusivity is 1.44 into 10 raised to minus 5 meters square per second. Hydrogen diffusivity in nitrogen is 6.74 into 10 raised to minus 5. Right? Hydrogen diffuses much faster, maybe something like 4.5 times faster. 4.5 times faster than carbon dioxide. Why does that? Why is that happen? Try to picturize, try to visualize. Imagine nitrogen molecules are there and a hydrogen molecule is diffusing by molecular motion, or a carbon dioxide molecule is diffusing by molecular motion. Carbon dioxide molecule is of course much bigger in size as compared to hydrogen molecule. So imagine that you are on a crowded street and let's say you are trying to go across the people on a crowded street, whereas let's say you carrying a big box trying to go across the street, you will obviously go much slower. So smaller the molecules, higher is the diffusivity. And if you look at the molecular weight, so molecular weight is 44 for carbon dioxide and molecular weight for hydrogen is 2. That means this ratio of molecular weights is 22. This diffusivity 4.5 times being faster, the ratio of diffusivity is proportional to approximately square root of the molecular weight ratio of the two gases. Okay, we'll see the scientific basis for this, and this forms a basis for many separation processes. For example, if you want to separate, let's say carbon dioxide, hydrogen from let's say air mixture, one of the ways to do that is to use a membrane. So you have a carbon dioxide, hydrogen, nitrogen mixture on one side, you have a membrane in between, and this carbon dioxide and hydrogen will permeate across the membrane. Now hydrogen permeation is going to be much faster because it's a small molecule as compared to carbon dioxide molecule, and this forms a basis for some of the membrane separations that you will see in semester 5. Other thing that I would like you to think about this same hydrogen diffusion in SF6, sulfur hexafluoride, or methane or nitrogen. Look at the diffusivity. Okay. As the molecular weight of the medium increases, diffusivity is reducing. Same gas, hydrogen, diffusing through SF6, higher molecular weight of the medium as compared to methane, lower molecular weight of the medium. Diffusivity is lower. Look at these two values. The reason that happens is, imagine again, you are trying to walk across a crowded street. Okay. That's one situation. Second situation is, imagine that you are trying to walk across a street crowded by elephants. You will obviously be walking much more slowly when there are elephants around. There is not much space to move as compared to if people are there. There is a lot of space to move about. So that's the reasons why this behavior is observed. So notice that the diffusivity depends not only on the component that is diffusing, but also the medium in which it is diffusing. Right. So that is with respect to diffusivity in gases. Just to talk to you about diffusivity in liquids. So you see the diffusivity values are much smaller. The diffusivity value is, in this particular case, 1.007 into 10 raised to minus 5 centimeter square per second. Right, into 10 raised to 5 gives you so many centimeter square per second. If you convert that into SI units, it will be 1.007 into 10 raised to minus 9 meter square per second. You see, obviously the diffusivity of substances in liquids is much lower. It was 10 raised to minus 5 here. It is now 10 raised to minus 9 in liquids. Right? Again, this is because the molecules in a liquid are so close to each other, there is very little space, and that's why the molecules moving tend to be much slower. They feel much more resistance when they are moving about with molecules which are crowded like a solvent in a liquid state. Okay. Again, you can notice that if you increase the temperature, the diffusivity is increasing. Okay. And here also you can see that of course the data is not enough, but you can see that as the molecular size reduces, diffusivity becomes faster. So that's similar to what we observe in case of gases. Okay, let's go forward. I want to talk to you briefly about diffusivity in solids in porous medium. Here is some data. Let's say these are diffusivity of different gases in different solid medium. So polybutadiene is like is a polymer, rubber, polyisoprene, polystyrene. So these are different polymers and diffusivity of gases in different polymers. So a couple of things you can see again, that diffusivity of smaller compounds is significantly larger as compared to diffusivity of bulkier molecules. These units are in 10 raised to minus 6 multiplied by this by 10 raised to minus 6 gives you in centimeter square per second. So this would be like 9.6 into 10 raised to minus 6 centimeter square per second. This is like 9.6 into 10 raised to minus 10 meter square per second. Or this is like 1.05 into 10 raised to minus 6 centimeter square per second, which is the same as 1.05 into 10 raised to minus 10 meter square per second. Look at these values: 0.06, 0.06 into 10 raised to minus 6 centimeter square per second, which is like 6 into 10 raised to minus 8 centimeter square per second, which is same as 6 into 10 raised to minus 12 meter square per second. Remember what I told you about diffusivity of substances in molecules in solid medium is significantly lower than that in liquids and that in vapors or that in gas state. Right? We had talked about this in our classes earlier. Second thing to look at is look at the this why this is important is because you can make membranes out of these polymers. So you might have a rubber membrane, silicon rubber membrane, or you might have a polybutadiene rubber membrane, and you will see that if it is a rubbery molecule, the chains can go further apart very easily, and then the diffusivity increases. Whereas if the polymer is crystalline, then the diffusivity values are significantly lower. So rubbery polymers versus crystalline polymers, or we should simply say, if you know a little bit about polymers, you may like to read, there's something called as a glass transition temperature. Above that it becomes in a rubbery state, below that it is in a crystalline state, and therefore the diffusivity is much more in a rubbery state because the chains of the polymer are more fluid, and therefore the molecule diffusing can easily push those chains apart and molecules can diffuse faster. That's why the diffusivity increases for rubbery polymers, and these are all important for membrane separations. You might want to separate nitrogen and oxygen to get you pure oxygen, right? For say, let's say for medical purposes, people who are having low oxygen partial pressure, like these virus cases, they have to be supplied with extra oxygen, and they have a pure oxygen or at least enriched oxygen mask for them to breathe easily and to get enough supply of oxygen into body. And one of the ways to separate oxygen from air is to put it through a membrane. You separate the oxygen from the nitrogen, at least get a enriched oxygen, maybe 25, 26, 30% oxygen. So gas separation in membranes is a very important operation, and then these kinds of polymers are very commonly used as a membrane for separating different gases. Let's go a little bit backward about the molecular origin of these different transport properties. Uh, when we talked about momentum transfer, we talked about viscosity, and there we saw that if you imagine a molecule going from one location to another location, and the variation of Vx as a function of y, we talked about the force per unit area exchanged as a result of collisions of molecules at any particular plane. And if z is the number of collisions per unit area, then the change of momentum, rate of change of momentum, would be the momentum associated with one molecules multiplied by number of such collisions happening per unit area. And then from kinetic theory of gases, we know these quantities z, number of collisions per unit area, and the mean free path lambda, the distance over which they go and collide, is related to 2 by 3 lambda. And then we could derive a relationship that the stress, right? So this is stress, this is nothing but force transmitted, it is nothing but rate of transfer of momentum per unit area. That's our stress, tau yx. And then you simplify, use Taylor series approximation for this Vx, and you get this expression. And then this we had defined, or this we had said, was the molecular viscosity, and this was our strain. This was like the driving force for momentum, driving force for momentum. So imagine that rho Vx is momentum per unit volume, okay? And then dy is the how rapidly or how fast this gradient exists, or what is the driving force for momentum over this length delta y. Same way, if we start thinking about now molecular origin of molecular diffusivity, right? So imagine that there is a substance A having a concentration Ca, and remember this Ca as a function of y, we are plotting Ca on the x-axis versus y. So at a location y, this is the value of Ca. At location y plus delta y, the value of Ca is slightly less. At a location y minus delta y, the value of Ca is larger. Now if you imagine that molecules are moving at random, and they go and collide, or they go and transfer, or they go and mix with the plane at y, the number of molecules traveling per unit area, if you like, gives rise to this velocity in the y direction. This velocity in y direction is arising out of the thermal motion, random thermal motion. So now the rate at which A goes from one location to another location is velocity multiplied by concentration at y minus delta y minus concentration at y plus delta y. Molecules are traveling from here to here, here to here, if you like. Okay. Now if you apply Taylor series again, Ca at y plus delta y would be at Ca at y plus delta y into dCA by dy at y plus delta y square divided by 2 factorial d square Ca by dy square at y plus so on, right? And we neglect all higher order terms because the delta y is really small. And now if you simplify, you will get the rate of transfer of A per unit area. This is nothing but flux. This is nothing but our driving force over this distance y. Okay. This now becomes our diffusivity, molecular diffusivity of A in this medium. I am writing it as dm, but what I actually mean is the diffusivity of A in this medium. DAB if you like, right? Compare our tau yx was minus 1 by 3 m n u bar lambda dvx by dy, okay? And this was the molecular viscosity. Mu was 1 by 3 rho u bar lambda. Now you compare these two. Now you will see that the molecular transport of viscosity and molecular transport of mass, they are analogous to each other. That's what I was trying to drive at. And same way when you do heat transfer, you will see the molecular origin of thermal conductivity would be something very similar. We are not going to do that, but it would be something similar. Now this allows us to estimate the values of diffusivity from kinetic theory of gases. So obviously it will be valid only if our gas behaves like an ideal gas, both A as well as the medium in which it is diffusing. If they behave like an ideal gas, then only this will be valid. Obviously it is not a reality, because molecules don't have a point mass. Molecules have a finite size, and therefore it does not predict the values accurately, but at least it tells us what is the logic, what is the rationale behind this behind this diffusivity of substances. Let's just quickly try to estimate what is the value of diffusivity using kinetic theory of gases. Okay, so here is a small problem. Just before you start doing this problem, let me just clarify a few things. So if you just substitute for u bar and lambda, you will find this is the expression for diffusivity. Now it is diffusivity of A in B, right? Therefore this M we replace by this expression. It's like an average molecular weight, okay? And this diameter of a molecule we replace by an average diameter of of the of the of the two gases, right? So these are the change because it is diffusion of A into B. Both A and B matter. Recall our discussion when we were talking about this discussion. Not only the size of A matters, but also the size of the medium B also matters. That's why we need to make these corrections for molecular weight as well as for diameters of A and B. Right? I would like you to calculate this, estimate diffusivity of hydrogen in nitrogen at 273 Kelvin, 1 atmosphere absolute pressure, and compare with experimentally measured value in the tables in the previous slide. That means this value. These are experimental observations. Hydrogen diffusivity in nitrogen, experimental observation is 6.74 into 10 raised to minus 5. Right? Experimental value is 6.74 into 10 raised to minus 5 meter square per second. I would like you to calculate this from this expression. Okay. Okay, let's see how we are going to calculate. Right. So diffusivity of A in B. Now we want diffusivity of hydrogen in nitrogen. So it is 2 by 3 square root RT by pi R 8314 T 273 divided by pi, okay, square root of 1 by molecular weight of A, molecular weight of hydrogen, 2 molecular weight of nitrogen, 28, okay, and 1 divided by root 2 pi half diameter of A, diameter of hydrogen molecule. It is 0.24 nanometers. So that is same as 2.4 angstroms, so which is same as 2.4 into 10 raised to minus 10 meters plus diameter of B, it is 3.54 into 10 raised to minus 10. So nitrogen, right? This whole thing square, and N, number of molecules per unit volume. How do we get number of molecules per unit volume from ideal gas? Number of molecules per unit volume is nothing but RT by P. Correct? No? No. If I say basis as one mole, right, say 1 gram mole or 1 kilomole if you like, that is 6.022 into 10 raised to 23, 10 raised to 26 molecules, because I have taken 1 kilomole. Okay, what would be the volume occupied by that 1 kilomole? Volume would be nRT by P, 1 into RT by P, right? So R would be 8314 into temperature 273 divided by pressure 1 atmosphere absolute 1.013 into 10 raised to 5, these many meter cube, right? 1 mole, 1 kilomole if you like. R we have taken in terms of joules per kilomole Kelvin, right? That's why I need to take this basis as 1 kilomole. So that means in this much amount of volume, these many molecules would be there, right? So number of molecules per unit volume would be 6.022 into 10 raised to 26 divided by this volume. This volume is RT by P. Okay, do that, put that here and calculate the value of molecular diffusivity according to kinetic theory of gases. You will get in terms of meter square per second. Just take care of units, okay, especially units of R. I'm again re-emphasizing. And once you calculate, compare with this value, compare this value and this value. Okay, you will know whether it is good or bad, or whether it is accurate or inaccurate. So pause this video, and do this problem for yourself. Don't go forward till you are satisfied, whether kinetic theory of gases works, does not work, accurate, not accurate. Of course you will know that it is not valid, because hydrogen and nitrogen, they don't behave like point masses, what is assumed in the kinetic theory of gases. So this value we are not going to get, but at least we are going to get something very close to this value. Okay, and people have proposed different modifications. Okay, let's go forward. I want to talk to you about a slightly different concept now. It is called as the Stokes-Einstein equation, or some people refer it as Einstein-Stokes equation. So imagine this is a gas containing some molecules A in some medium, in medium B, right? Like it could be hydrogen and nitrogen, and it's a very dilute solution, right? That means mole fraction of A is very small. So I have very few molecules of A and large number of molecules of B, and there is no bulk motion, so it is a stagnant situation, right? Let's say this is our x direction. Ca is the concentration of A at this location. Ca is the concentration at this location. Obviously Ca is a function of x. That's what we want to consider. What I want you to consider is write an expression for the diffusivity. That's where we are going to go, and that's how this equation tells us how diffusivity changes with the viscosity of the gas. Okay. Let's talk about this. Okay. Now, if concentration of A is different here and concentration of A is different here, this concentration difference gives rise to an osmotic pressure difference. Now remember, we were talking about osmosis and osmotic pressure difference. Say, let's say one case you have a salt solution 2%, another case you have salt solution 7%. Now osmosis is the process by which water will go from the 2% solution to 7% solution, because that osmotic pressure is larger, and therefore the water molecules will diffuse, it will dilute that 7% solution. And reverse osmosis is the process by which you can reverse this process. So the osmotic pressure difference tells us that there is a driving force for this diffusion. That is the driving force. That pressure difference is going to act on these molecules of A. If you like, you can also think about this in terms of chemical potential. You may not like to think in terms of osmotic pressure because it's not a liquid solution, it's a gas now. Okay, but you can also think in terms of it as a liquid solution, right? It could be gas. I don't need to really think in terms of gas, I need to really think in terms of just a solution. So if it is a liquid, it is easier to think in terms of osmotic pressure, or you might like to think in terms of chemical potential, fugacity if you like. And this is what you're going to do in your thermodynamics course, chemical engineering thermodynamics. You may have already done it partly. Okay. So this osmotic pressure or the chemical potential difference leads to a driving force on these molecules of A. Now when these molecules of A are moving about, let's say under this driving force, they have to diffuse through this medium B. And if you think about a molecule that is here, molecule is diffusing is equivalent to molecule being stationary and the medium going across it. So there is a drag force that each diffusing molecule experiences. So there is a drag force experienced by diffusing molecules, and the osmotic pressure is a driving force for pushing molecules from left to right in this particular case, and drag force is from right to left arising out of the medium B through which it is diffusing. At steady state, these two driving forces and the opposing force, they would be equal. That will give rise to a steady state concentration difference or a steady state flux of A in this medium B. This flux is decided by a steady state between these forces. That flux will decide the net, that these driving force and the opposing force, drag force, will decide the net resultant flux of A from location 1. Let's say this is our location 1 to location 2. A1 is at one is having high Ca, 2 is having low Ca. What I want you to do is I will to quantify all these things. Okay, let's go forward. What I want you to write is, first of all, what is the force per unit area arising out of this osmotic pressure. Then second thing I want you to write is what is the force per unit mole of the solute A. Then I would like you to write what is the force per unit molecule of A. And then what I would like you to write is the drag force on the molecule of diameter d moving with a velocity v through this medium, Stokes law, because remember the diameter is so small, angstroms, nanometers, right? So Stokes law is valid. Archimedes number for a molecule is far less than 18, far less than 1 if you like. So drag force can be calculated based on Stokes law. Okay. Once you write that, I would like you to equate the driving force and the drag force. Okay. And then get an expression for flux of A. Pause this video, do it for yourself. Doesn't matter even if you don't get the correct answer just now, but the thought process is what is important. Therefore pause the video and do it for yourself. Okay, here is the answer. Okay. Driving force per unit volume is d pi by dx, and if you remember from your 11th standard, 12th standard, how osmotic pressure is related concentration of A. This relationship is called as Van 't Hoff equation. That tells you that osmotic pressure is nothing but concentration of A multiplied by RT. Recall. Go and see for yourself if you don't recall. So if this is the pressure per, if this is the driving force per unit volume, Newton per meter cube, Ca is the concentration, then the force per unit mole would be 1 upon Ca d pi by dx. This is per mole. I need to divide by Avogadro's number to get a force per unit molecule. So this is our Avogadro number. Think about this. Make sure that you are convinced about this. What is the drag force now? Stokes law. 3 pi d viscosity of the medium B and velocity with which these molecules move. Now if I equate these two, what will I get? I'll get this expression. Now flux of air, I can rearrange this little bit, bring this Ca on this side and bring all these things on the other side. Ca into V is nothing but concentration, moles per unit volume multiplied by the velocity. It is nothing but volumetric flow rate per unit area. This tells us the flux of A, kilomoles per meter square per second. Flux of A. Now if you rearrange, use Van 't Hoff equation, you will get this expression. Now this you can compare with Fick's law and you will find that the diffusivity is RT divided by Avogadro number 3 pi d mu. Right? So this dA mu by T, dA mu by T, I bring the mu here, bring the T here. dA mu by T is constant and that constant is R divided by Avogadro number 3 pi d. So if D is larger, molecules are of a larger size in the same medium, diffusivity will be lower. And this dA by mu being constant, there is another name for it, it's called as the Wilke-Chang equation. Later they derived it based on some other principles, some other concepts, but this is what is used very commonly to estimate diffusivity at different temperatures. So if I give you at different temperatures, so if I give you diffusivity at let's say 30 degrees centigrade and I ask you the diffusivity at let's say 50 degrees centigrade, then I can relate from this equation. All I have to worry about is the temperature difference and the viscosity of the medium. It is the drag force exerted by the medium. So this mu is viscosity of the medium. Medium is B and D is the diameter of the molecule. Diameter of molecule of A. What is diffusing? Solute and the medium. Okay. So this is how one can relate diffusivity at different temperatures. You will need to do these kinds of things when you start going to semester 5 and semester 6 and so on, how membranes would behave at different temperatures. So these are typically calculated based on diffusivity changes in the medium. Okay. A couple of points I would like to bring to your attention. Remember when we were talking about wet and dry bulb temperature, we had a dry bulb, we have a wet bulb. This temperature was TW and we wrote rate of heat transfer to wet bulb as heat transfer coefficient multiplied by area multiplied by the temperature difference T minus TW. Heat is being transferred from the surrounding air to the wet bulb. Heat transfer from air to wet bulb. And we talked about driving force for mass transfer. If you don't recall, go and revisit the MEBC lectures. Mass transfer is from water vapor, is from the wet bulb to the air. And then that rate of mass transfer we wrote in terms of mass transfer coefficient into area multiplied by the humidity difference between the wet bulb temperature minus the humidity of the air. And then we equated them, because this much amount of heat being transferred divided by lambda, latent heat of vaporization of liquid water, will tell us the mass transfer rate. And then based on that we got this expression. And that time I just told you that this H by kg is Cp for this humid air. So this allowed us to get Hw minus H would be equal to Cp of dry air plus H times Cp of water vapor divided by lambda at the wet bulb conditions multiplied by T minus T wet bulb. This formula we derived because I just simply told you that this H by kg is Cp. Let's now start talking more in terms of what this H by kg is. It is a ratio of heat transfer coefficient divided by mass transfer coefficient. It's not a dimensionless number. It is not a dimensionless number. And this I had simply told you was Cp. You have to believe me at that point of time. Right now, you know little bit about mass transfer. We can start talking about that. Okay? Think, pause this video, think how this can be equal to Cp. Just think for yourself and see whether you can prove that H by kg is Cp. Here's the answer. Remember we talked about analogies. Let's take any one of the analogies. Let's take for example this Chilton-Coolburn analogy. What does this tell you? That Sherwood number is like this, Nusselt number is like this, and Nusselt number can be is related to heat transfer coefficient, Sherwood number is related to mass transfer coefficient, right? So if I want to take now ratio of this heat transfer coefficient to mass transfer coefficient, what can we do? One thing we can do, this is our Nusselt number is f by 2, Reynolds number into Prandtl number raised to 1 by 3, Sherwood number f by 2, Reynolds number into Schmidt number raised to 1 by 2. I can take this ratio. Okay? We define Lewis number as another dimensionless number as Schmidt number divided by Prandtl number. Just it will be clear to you in a minute. Okay? Think about what is the meaning of Lewis number in terms of the thickness of the concentration boundary layer versus thermal boundary layer. Remember, Schmidt number is a ratio of boundary layer thicknesses. Prandtl number is a ratio of boundary layer thicknesses of what? Try to recall. Okay. Then think about what is the meaning of Lewis number. Okay. So Lewis number would be alpha thermal diffusivity by molecular diffusivity. It is a ratio of thermal diffusivity divided by molecular diffusivity for mass. Thermal diffusivity for enthalpy, molecular diffusivity for mass. Okay. It is just, you have to just substitute Lewis number is Schmidt number. Schmidt number is mu divided by diffusivity and rho divided by Prandtl number. Right? Prandtl number is Cp mu by K. K I am bringing on the numerator. Okay. So mu will cancel. K by rho Cp, that's thermal diffusivity divided by now molecular diffusivity. That's the meaning of Lewis number. Think in terms of the boundary layer thicknesses. Now let's go forward. Can I take ratio from here? Nusselt number by Sherwood number. Can I take this ratio? That would be Prandtl number divided by Schmidt number raised to 1 by 3, which is same as 1 by Lewis number raised to 1 by 3. Go forward. simplify. Nusselt number is now, we want Nusselt number divided by Sherwood number. This is same as 1 by Lewis number raised to 1 by 3. What is Nusselt number? H D by thermal conductivity. What is Sherwood number? Mass transfer coefficient, D divided by molecular diffusivity. Right? So now H by kg, you can write, this D will cancel out. H by kg, so Nusselt number by Sherwood number is same as 1 by Lewis number raised to 1 by 3, and I am just writing it again. It is H divided by thermal conductivity, molecular mass transfer coefficient multiplied by molecular diffusivity. So H by kg would be thermal conductivity divided by molecular diffusivity into 1 by Lewis number raised to 1 by 3. I can simplify this little bit further. Let me just show it to you. This is going to tell us that H by kg is 1 by Lewis number raised to 1 by 3 multiplied by thermal conductivity divided by molecular diffusivity. Right? Let me divide by rho Cp and multiply by rho Cp. So thermal conductivity divided by rho Cp is nothing but alpha. So this is nothing but alpha rho Cp divided by molecular diffusivity. And remember, alpha by dm is your Lewis number. So therefore, H by kg is Lewis number raised to 2 by 3 multiplied by rho Cp. Now you see, for air and water vapor, you calculate alpha, you calculate you calculate the diffusivity. Alpha by dm is Lewis number is almost equal to 1, and therefore for air and water vapor we said H by kg is nearly equal to Cp. Rho is also the same. Rho just takes care of the unit, because units of H and kg, and we have talked about humidity per unit mass, and therefore that rho is coming, right? This is valid only because Lewis number is almost equal to 1, or Lewis number raised to 2 by 3 is almost equal to 1. That happens only for air and water vapor. If you talk about anything else, let's say you have acetone vapors diffusing in let's say nitrogen, right? You are drying something from a liquid, solid containing liquid acetone. Let's say you are crystallizing from acetone, so your wet crystals contain liquid acetone, and you are drying using hot nitrogen. So there is heat transfer from nitrogen to the surface of the solid, and there is vaporization of acetone from the solid surface into the hot nitrogen, and therefore this Lewis number will come into picture. We can estimate one from the other. If I estimate heat transfer coefficient, if I measure heat transfer coefficient, I can calculate mass transfer coefficient, because they are related to by each other through Lewis number. Lewis number is a physical property, is a property of the medium. It's a number fixed for that particular case. Or if I know the mass transfer coefficient, I can estimate heat transfer coefficient. That's the importance of Lewis number. Okay? Think about all this. Think about what we have done so far. Think about what we have. Something that I would like you to think about is how this mass transfer is going to be important in different operations in your next semester, semester 4 and semester 5. And many of the things that chemical engineers do is to separate compounds, and these are called as separation processes or mass transfer operations. So you are going to do an operation called as absorption, in which, let's say we have air containing a pollutant, let's say ammonia, in the gas phase. Now we want to take out this ammonia. One way of doing that is to contact with a liquid, water. So if I take water and I contact this gas, ammonia will diffuse, ammonia will transfer from the gas to the liquid. Now if you imagine, gas is like this and liquid is like this is our interface. Now if I write in terms of location, right, this is our location, if I write in terms of partial pressure of ammonia, now partial pressure of ammonia will reduce because it is getting transferred, it is to the liquid side. Now I can imagine a boundary layer. If I plot concentration as a function of distance, partial pressure as a function of distance, I can think about this as a boundary layer. I can think of this as a film, resistance to mass transfer. At the liquid interface, it will dissolve. And then if I plot concentration of ammonia in liquid phase with respect to distance away from the interface, it will reduce. Okay, mass transfer. So there is a net transfer from ammonia from gas phase into liquid phase. That's how this ammonia gets absorbed into water. I can remove ammonia from the gas by contacting it with liquid water. This interface is at equilibrium. That means the partial pressure of ammonia in the gas phase at the interface is in equilibrium with concentration of concentration of ammonia in the liquid at the interface. It is on either side of the interface, gas side of the interface and liquid side of the interface. This equilibrium, solubility, is how you are going to describe this equilibrium. Henry's constant. You are going to learn about equilibrium in your thermodynamics course. So this is going to be done in your Chem-Eng thermodynamics course. Mass transfer, boundary layer, rate of mass transfer tells you how fast I can absorb. Rate of mass transfer is something that we have done in momentum and mass transfer. Together, these two things together is going to allow you to design an absorber. So therefore, once this semester ends, don't forget everything about mass transfer. Don't forget everything about thermodynamics, because both these things are going to be required for you to do design of different chemical engineering operations, mass transfer operation. Absorption is one of them. We talked about several other such operations as we had gone in our first semester second MEBC course as well. We had talked about cooling tower or humidification, or we had talked about dehumidification. What was humidification? What we did in cooling tower? We sprayed hot water and we contacted with air. This air got humidified, and because the liquid temperature was more than the wet bulb temperature, liquid cooled down. That's how we used cooling tower. Air got humidified. So if I think in terms of the liquid and gas, now gas contains air, liquid is water. Now at the interface, partial pressure would be equal to vapor pressure, equilibrium, and then there is a driving force, mass transfer of water vapor from the droplet to the air gets humidified. Mass transfer and thermodynamics both together are required to design a cooling tower. Same way dehumidification, I contacted with cold water, water below the wet bulb temperature, and air got dehumidified. Now mass is being transferred from the air into the water. Partial pressure is more than the vapor pressure at the liquid temperature. This is your driving force. This equilibrium between the liquid temperature and the vapor pressure is given by thermodynamics, right? You are going to do distillation, you are going to do membrane separation, you are going to do crystallization, you are going to do adsorption, ion exchange. Okay? not going to go into details of each one of them. Just I'm going to give you a table. Okay? Gas absorption. We transfer solute gas from the gas phase to the liquid phase. Mass transfer. The driving forces are dictated by equilibrium at the interface, solubility of gas in liquid, ammonia in water. That is decided by Henry's constant. This is going to come in your Chem-Eng thermodynamics course. This is going to come in your, it has already come in your MMT course. Together, it is going to allow you to design your separation processes. That's going to come in semester 4 and semester 5. So in semester 4 and semester 5, you can't afford to forget momentum and mass transfer. It is the very backbone of whole chemical engineering operations. You can't forget Chem-Eng thermodynamics. Extraction we talked about when we were doing MEBC. Solute, let's say P, from one liquid phase, aqueous phase, was getting transferred into another immiscible liquid phase, organic phase. We talked about equilibrium as distribution coefficient, right? Mass transfer. Distillation, more volatile component goes from liquid to vapor and less volatile goes from vapor to liquid. It is decided by interface. Mass interface is at equilibrium between the vapor and the liquid. That is decided by relative volatility, modified Raoult's law if you like. You are going to do that in your thermodynamics course. Crystallization, we did that in MEBC, right? Supersaturated solution, cooling, I get supersaturated solution, crystals come out in the solid phase. Mass transfer is of the solute from the supersaturated liquid to the crystal surface. And thermodynamics dictates the solubility, equilibrium. Right? That's how important thermodynamics is. That's how important the mass transfer is, because we have to design all these operations. Drying, I was drying solid crystals by vaporization of water. Water is getting transferred from in the liquid phase from the solid mass into the vapor. It is dictated by the vapor pressure at the temperature of the liquid, equilibrium. Humidification, dehumidification we talked about. Adsorption and ion exchange. Adsorption, something is getting adsorbed from the fluid phase into the solid phase, carbon if you like. It is dictated by adsorption isotherm, again dictated by thermodynamics. Okay. Membrane separation, we'll talk more about this in semester 5 when you start doing separation processes. So point I want to emphasize is all the separation processes that chemical engineers do to separate different components, and that's a very important thing that chemical engineers do, different from all the other engineers. The very backbone of these separation processes is mass transfer and thermodynamics. You need both of them to design these operations. Don't forget both these courses ever in your life. Just to give you a strategy, how do we solve these mass transfer problems? Okay, sometimes these problems can be very challenging. You might find that some of these problems are very difficult. Here is a strategy. First of all, think, where is mass transfer taking place? From which location? From which phase? Identify the concentration driving force for mass transfer. What is the mechanism of mass transfer? Is it convection? Is it diffusion? Is it turbulence? Any of the any two out of these three, or all three, or any one of the three? Which strategy would you like to adopt? Microscopic? Macroscopic? How do I get a value of K? Empirical equation? Theory? Analogy? How does mass transfer affect system properties with respect to time, like our sugar problem or a drug problem, or location, like our pipe problem? Okay, think about, revisit all the problems that we have done so far. Write this down in your notebook. Write this down. Look at all the problems that we have done for mass transfer. You will see these are the steps that we have followed. So if you follow these steps, you will get the answer without any difficulty. Okay. We stop here for mass transfer. we stop here for mass transfer. That completes our syllabus as well. Last thing I would like you to do, we have talked about dimensionless numbers, we have talked about scaling all the time. It's very important. These dimensionless numbers are very important. List out all the dimensionless numbers that we have used so far. That's point number one. Scaling. We have always scaled our equations. That has allowed us to calculate many things. That has allowed us to get an insight. That has allowed us to apply it to somewhere else. Okay. Plug flow concept. Mass transfer concepts. Diffusion in presence of a stagnant beam. Log mean concentration driving force. Number of transfer units, height of transfer unit. In momentum transfer, if you want to think, drag coefficients, terminal velocity, head number, flow number, best efficiency point, Bernoulli equation, so fluidization, so many concepts we have covered. Make a separate sheet, separate notebook or a diary if you like. Just list out the main concepts that we have done. Okay. And these are going to come in handy for our functioning as a professional chemical engineer. And if you are understanding these concepts, all future courses as well as future applications of these concepts, if you keep them handy in one place, it is so much easier. If you could keep them in one place, have a look at it again and again, go to another class, go to next subject, try to look back, when did we do this concept? You've got all the concepts that you need for chemical engineer to function as a chemical engineer. Henceforth, it is just an application. You are 100% chemical engineer now, provided you understand all these concepts and you're able to apply. Okay. Other years you're going to learn, of course, you're going to learn more concepts about different things. Process control is something that you have not done. For example, separation process. There are many more concepts that are coming there, but the principles are what we have discussed in this class. Okay. So make a separate list of all the concepts right from day one in this course you have studied. It will help you to sort of grasp the subject better, and it will help you to appreciate and apply these concepts when you go to when you start functioning as a chemical engineer, as well as when you go to higher classes and other subjects. So we stop here. Our course ends here. Our learning of momentum and mass transfer does not end here. Course ends. Our learning does not end here. As we go along, these concepts will get reinforced. You will appreciate them better as you start using them. So only when you use them, use it again and again and again, third year, fourth year, masters, PhD, when you function as a chemical engineer in industry, in R&D, when you use them again and again, all this learning will become more and more perfected. Okay? That's when the learning of momentum and mass transfer gets complete, not with the end of semester. Okay? That's all what I wanted to cover in this course. Happy studying, happy learning momentum and mass transfer. Enjoy, and try to see the applicability of all these concepts that we have studied. Enjoy, learn for the sake of learning, learn for the sake of enjoyment, for the thrill that you've learned something new, you've learned it to apply it to some new situation. That's the thrill, not the subject, not the marks, not the CAT, not the midsem, not the grades, not the CGPA. We'll stop here now.